Students, we're talking about the different techniques of digital to analog conversion. Went through ASK, we also discussed the FSK. Now let's talk about the third one, which is the PSK or the phase shift keying. Students, in this particular case, the phase of the carrier signal is varied, while the amplitude and the frequency, they remain constant. Students, PSK is relatively common than ASK and FSK. आप देखेंगे कि जब हम quadrature amplitude modulation या फिर QAM पढ़ेंगे, which is our fourth and the last technique for digital to analog conversion, you'll see that that is the most commonly used technique so far. But if you compare ASK, FSK, and PSK, PSK is probably the most common out of the three. Students, once again on the slide, you can see that we have got a bit rate of 5, we have got a baud rate of 5 as well. We have got a modulated signal in which our signal takes two different forms. Two signal elements, one with a phase of 0. So you've got a 1 with a phase of 0 degrees. And then you've got a 0 which has got a phase of 180 degrees. So you're essentially varying the phase of the carrier signal, and the modulated signal, the resulting modulated signal that you get has got different phases, varying phases for the two signal elements that we are using, but the amplitude remains the same once again. So amplitude is constant, and as you can see, the frequency is constant as well. The number of cycles completed per second is constant as well for both the signal elements 0 and 1. Students, the bandwidth is exactly the same as that of ASK. So the bandwidth of PSK, binary PSK, binary because it just uses two signal elements, 0 and 1, the bandwidth of PSK is equal to the bandwidth of ASK, and it's lesser than that of the required bandwidth of the FSK, frequency shift keying. अब students, देखेंगे implementation binary phase shift keying की. Once again, we have got an oscillator, as you can see. Oscillator produces a carrier signal. In this particular case, we have got the polar NRZ signal. So we are not using bipolar, we have got a polar. So our digital data that we need to send is represented by a polar NRZ line coding scheme. Now students, in this particular case, the carrier signal is generated once again, and for 0 we have, for 1 we have a phase of 0 degrees. No change in amplitude, no change in frequency, and the phase remains constant as well, no variation. Now students, जैसे ही we'll get a 0, the phase changes. So a 1 is represented by a phase of 0 degrees, and a 0 is represented by a phase of 180 degrees. Once again, we have got a 1, a phase of 0 degrees. We have got a 1, a phase of 0 degrees, and the phase varies as soon as we encounter a 0, and we have got a phase of 180 degrees. So your carrier actually helps us to generate this polar NRZ signal, and the modulated signal that we get has got a different phase for each one of the two signal elements that we are using in binary PSK. Now students, because this is a simple technique, as you must have noticed, the designers decided to use 2 bits at a time in each signal element, and that decreased the baud rate, decreased your signal rate, and therefore it decreased the required bandwidth as well. And we call this technique as quadrature PSK or QPSK, as you can see. In this case, students, we use 2 separate binary PSK modulations. The first one is on the top. So basically, as you can see, we have got 2 bits per signal element in this case, and we are using 2 binary PSKs. This is our binary PSK1 modulation, and then you've got our binary PSK2 modulation. We still have a 2x1 converter, and we have got an oscillator that's producing our carrier frequency. There is a phase shift between the carriers produced by the first oscillator. There is a different phase which is produced in the carrier, which is produced by the second part of the oscillator, and ultimately when you sum them up, you get your modulated signal for this quadrature PSK. And students, as you can see, we are still getting composite signals, but the two composite signals that are created by each multiplier, one here and one here, the two composite signals are this one and this one, and these two composite signals are once again sine waves with the same frequency, the same amplitude, but different phases. And when they are added, the result is another sine wave. So this is your summation. Result is another sine wave, and it has got one of the four possible phases, which can be 45 degrees, 135 degrees, minus 45, and minus 35 out here that you're going to use in this quadrature PSK digital to analog conversion technique. Students, example karenge. In this particular example, we have a bandwidth for a signal that is transmitting at 12 megabits per second for QPSK, and the value of D is equal to 0. Now the formula for QPSK, because we know that 2 bits are carried by one signal element, R in this particular case is 2. Now the signal rate or the baud rate is N divided by R, and that comes out to be 12 megabits per second divided by 2, which is equal to 6 mega baud. And if our D is equal to 0 now, then we can see that our bandwidth is equal to S, which is equal to 6 megahertz in this particular case. So in the case of quadrature PSK, we have reduced the bandwidth to half of the bit rate, which is 12 megabits per second, and we have reduced it to 6 megahertz per second, and it is proportional to our signal rate as well.